Hello friends, in this series of lecture pertaining to the course on high temperature materials, we have so far been considering the behavior of material at high temperature. So to give a brief overview of what we saw till now, we began by considering began by introducing what an high temperature is in the context of the application. So we gave different definitions for the high temperature, largely in the context of the material that is being used in a particular application. So based on the property of the material, we gave different definitions for high temperature. And once we defined high temperature, we began by comparing the change in the properties of the material at high temperature with respect to that of the ambient temperature. So we began with the definition of high temperature, then we consider the change in the properties of the material at high temperature. Then we moved on to considering the behavior of the material at high temperature with respect to that of the ambient temperature. In order to study the behavior, we focused largely on the mechanical behavior of the material. And in that mechanical behavior, we restricted ourselves to creep behavior because this was the most relevant one to the application. So the creep we defined as the time-dependent behavior of the material to an imposed mechanical condition. So this time-dependent behavior to an imposed mechanical condition becomes more pronounced at high temperature, and this is what governs the applicability of the material at high temperature. And that is the reason why we largely focused on understanding the creep behavior of the material. So creep behavior can also be vaguely related to that of the mechanical response of the material to a given condition, and this condition involves both stress or mechanical load and the high temperature. And after that, we moved into considering how the surface of the material that is being used in an application, or high temperature application to be more specific, reacts to the given environment. So you have a given environment, and because of the high temperature, the reaction of a material to the given environment varies, and this we saw in the previous lectures. And in that, we did not consider all the different reactions as we would do for in case of a corrosion corrosion. We did not do that. We largely confined ourselves to oxidation of not all materials but metals at high temperature, and we saw what are the factors governing the oxidation and what are the different rates in which the material oxidizes. Now, in these lectures, or in the few lectures that remain, we will be focusing on how to increase or enhance the behavior of the material at high temperature. So what we essentially want to do is we want to see how one can increase the life of the material at high temperature. So far, the large amount of consideration that we have been giving to the behavior of the material at high temperature, both in terms of its properties and in terms of its behavior, both mechanical behavior and surface behavior. So all these we have been doing largely from a theoretical point of view. We have been just considering different theories and how these theories relate to, or how these theories can help us understand the behavior of the material at high temperature. Now we will move away from, or slightly move away from, the theoretical consideration, and we will look things from a different perspective, that is from an application point of view. We will see how we can enhance the behavior of the material at the high temperature. Particularly, we want to see how one can increase the life of the material at high temperature. So this would be the focus of the few lectures that remain. When we want to consider the life of the material, we again have to go back to the creep behavior of the material, because this is what dictates the life of the material at high temperature. And when we want to consider the creep behavior of the material, there is no better way than by considering the strain versus time plot, because this plot is rather consistent with the definition of the creep, and it also helps us understand what are the factors that, or what are the stages that govern the life of the material at high temperature. So let us get back to the basics and let us see what actually do we mean by the life of the material, or what should we have to enhance in order to increase the life of the material at high temperature. So if you could recollect the result of a creep testing, or the outcomes of it, we represent it in terms of strain versus time. Now when we consider strain versus time, this is consistent with the definition of the creep, and which is nothing but the time dependent response of the material to a given mechanical condition. The mechanical condition is constant, and we want to see the response of the material as the time progresses, and this is critically important at high temperature, and that is the reason why, even though there are other ways of representing the creep results or the outcomes of the creep testing, we stick with this representation wherein you have strain and time. Now, conventionally or largely, the behavior of the material, particularly when we say material, metals and alloys, the behavior of metals and alloys at high temperature during creep testing, they follow a particular pattern. So we saw these pattern can be represented in this manner. You have an instantaneous creep region and a transient creep region. So instantaneous creep region is rather instantaneous. There is a linear relationship, sort of a linear relationship between the strain and the time. And there is a region which we refer to as the transient creep region, where the rate at which the strain occurs, it is gradually decreasing, and there is a region wherein there is not much strain observed and the strain rate is rather minimal, and there is a final region where there is a significant increase in the strain rate and ultimately the material fails. So you have your first region, which we refer to as the instantaneous creep region or the instantaneous strain, because again, when we talk about creep testing, we are not gradually increasing or applying the stress to the material, we are instantaneously applying the constant load to the material. So in that case, you have an instantaneous strain, and that is what we refer to as the instantaneous creep. And after this instantaneous creep, what you have is a gradual change in the slope of this curve. So what we mean by the slope of this curve is nothing but the creep rate. So there is a gradual decrease in the creep rate, and this is what we refer to as the decelerating creep region or a transient creep region. So the reason we call this as a transient creep is because it relates two different creep states. One is the instantaneous creep and the other creep state here. So that is the reason why we refer to this as the transient creep, and the other name for this is a decelerating creep. As you can see, there is a gradual decrease in the rate of creep that you observe. And the stage that follows the transient creep region is a state wherein the deformation or the strain is rather minimal, and the rate at which it occurs is also minimal. So there is only a marginal amount of deformation that is observed in this particular stage, and this stage we refer to as the steady state creep stage. So this state is the steady state creep stage, and final stage wherein there is a significant increase in the rate of the strain. And a significant increase in the strain, we refer to it as the accelerating or tertiary creep stage. So we have primary creep that includes instantaneous and transient creep. We have secondary creep that is largely steady state creep, and finally we have our tertiary creep, which is also an accelerating creep, and accelerating creep is largely ignored because once, particularly since we are since we are treating this whole creep behavior from the application point of view, once you have a significant amount of strain that sets in after a prolonged period of minimal amount of strain. Let me repeat, once you have a significant amount of strain set in after a prolonged period of minimal strain, it means the system or the material has entered into the tertiary creep and eventually it will fail. So therefore, in an application, once people start to observe a significant increase in the strain after a prolonged period of minimal strain, then it is time for that particular material to be replaced. That is the reason why this particular stage of the creep is usually overlooked. So we are then left with the instantaneous creep, the transient creep, and the steady state creep. Now, our interest in these series of lectures is to prolong the life of the material. We want to extend the life of the material. So if you consider the creep curve, particularly the time, different stages they spend during the creep testing, or the duration associated with each of these stages during the creep testing, as the name itself reflects, the instantaneous creep is rather instantaneous. So if I refer to this as TMM, this time taken for the instantaneous creep is significantly lower than the overall time taken for the creep failure of the material. So this we have seen much earlier as well. So when you consider exclusively in terms of the time spent by the material on different stages, the instantaneous creep, it doesn't contribute to the life or the overall life of the material. And similarly, the same more or less goes for the time spent in the transient creep, because transient creep, it just relays the instantaneous creep to that of the steady state creep. So in that case, the time spent even under the transient creep is not as comparable, it's not of the same order of the time spent under the steady state creep. So the transient creep, the time spent under the transient creep is also not as much as the time spent by the material under the steady state condition. So even though the time spent under the instantaneous creep is much lower than that of the transient creep, when compared to the time spent by the material in the steady state condition, both these do not play a significant role. Therefore, the material in its application, particularly the high temperature application, spends most of its time in steady state condition. So therefore, if we are able to prolong the time spent by the material in the steady state condition, we can ultimately increase the life of the material at high temperature. So therefore, the first aim of our study, or whatever, so if we are an engineer who wants to supply a material for an application, high temperature application, and we want to enhance the creep behavior of the material. So when we say we want to enhance the creep behavior, what we essentially mean is that we want to increase the life of the material at the high temperature. So what then we need to do is increase the time spent by the material in steady state creep. So the larger the material spends time in a steady state creep, the larger will be the life of the material in its high temperature application. So therefore, our aim, even though from a comprehensive, from a ladder, when you consider the holistically, when you want to talk in terms of the application, even though we say that we want to increase the life of the material, what we essentially mean is we want to prolong the duration of the steady state creep. Now, when we want to prolong the duration of the steady state creep, so what we essentially mean is that even though, as we refer to the steady state creep as a region wherein the strain is minimal and the region wherein the strain rate is very low, close to zero, there is a significant, there is some amount of strain that is associated with the steady state creep. So generally, even though we relate or we characterize the steady state creep as a region wherein there is a minimal strain, we cannot say there is a zero strain. There is of course some minimal strain. So generally, the curve is represented in this manner. So when compared to the creep rate here, when you compare to the creep rate here, so in these zones, when you compare to the creep rate in this zone and in this zone and finally in this zone, the creep rate in this steady state zone is rather significantly reduced. But there is still some amount of strain that is experienced by the material in this creep, steady state creep. Now, when we say we want to prolong the time spent by the material in the steady state creep, one way of doing that is by reducing the amount of strain experienced by or exhibited by the material over the given period of time. So what we mean by that is, supposing I reduce the amount of strain exhibited by the material over this over a specific period of time, then one way of the way this particular plot, this strain versus time plot, would change is you would have more or less the same instantaneous and transient creep, but now I want to prolong, or now I want to reduce the amount of strain that is experienced by the material. So therefore, now this section would change, and finally the tertiary creep would set in. So what we have essentially done is we have essentially reduced the amount of plastic strain exhibited by the material at a given instance. So when you consider, say, this particular instance, T1, the amount of strain exhibited by the material here is much less than the amount of strain exhibited by the material here. So when you compare these 2 points at a given instant, the amount of strain, plastic strain exhibited by the material at this point in the green curve is much lower than in the red curve. So both these are in the steady state condition, but amount of strain we have significantly reduced. So this way, when you reduce the amount of strain at a given point, what you are essentially doing is you are reducing the slope of the curve in the steady state region. Already in the steady state region, when compared to all the other regions, the slope of the curve is minimal. We refer to that as that's the reason why we refer to as the steady state creep. There is a minimal amount of strain experienced by the material in the steady state creep, and this minimal amount of strain leads to a definite creep rate. And this creep rate, if it is reduced, then you can ultimately prolong the life of the material. So that is what we would essentially like to do. We want to reduce the amount of strain exhibited by the material at a given point of time within the steady state creep. And once you do that, you are reducing the rate at which the strain is experienced by the material within the steady state creep. So essentially then what you are doing is you are reducing the steady state creep rate. So we saw that the way to prolong the life of the material in high temperature application is to increase the time spent by the material in the steady state creep. And one way of doing that is to reduce the strain exhibited by the material at a given point in the steady state creep condition. And when you do that, when you reduce the strain exhibited by the material in the steady state creep condition, what you are essentially doing is you are reducing the steady state creep rate. You already have a reduced steady state creep rate when compared to the other stages of the creep, and even you are reducing the rate of the creep in the steady state condition, thereby prolonging the time spent by the material in the steady state condition. So that is what essentially we want to do. We want to reduce the creep rate exhibited by the material, the minimal creep rate which is already reduced. We want to further reduce it in the steady state condition. When we further reduce it, we ultimately prolong the time spent by the material in the steady state condition, thereby increasing the life of the material at high temperature. So our goal now is reduce the strain exhibited by the material at a given point in the steady state condition. So by reducing the strain at a given point in the steady state condition, we are reducing the overall creep rate in the steady state condition. This increases the time spent by the material in the steady state condition, thereby increasing the life of the material. So this is what we would like to do. We would like to reduce the plastic strain exhibited by the material within the steady state condition. Now, if you could recollect what essentially happens in the steady state condition. So this steady state condition is preceded by the transient creep. So what happens in the transient creep is that largely there is a plastic deformation that's introduced because of the stress. So when you consider a creep testing, you hold the stress and the temperature to be constant. Now when you hold the stress to be constant, because of the stress, there is a significant amount, as the time increases, there is a significant amount of plastic deformation that is being introduced. The reason we want to study, if you could recollect, we spent some time on studying the transient creep. In addition to the steady state creep, we spent some time studying the transient creep because the amount of strain that is introduced during the life of the material at high temperature is largely due to the instantaneous and transient creep. So therefore, the strain is introduced during the transient creep, the stage that precedes the steady state creep. In that stage, what happens is that when you say that there is a plastic deformation observed, so it means this stage introduces, or rather increases the dislocation density. So in this stage, a significant amount of dislocation is introduced, significant amount of dislocation is made active, and these dislocations, they travel, and since there is a large number of dislocation and they interact, what you essentially observe is strain hardening in this region. So the reason for the decelerating creep is because you have a dominance of strain hardening. So similar to your regular tensile behavior, your regular plastic deformation, you have increase in the number of dislocation, and these dislocation interact, and to add to the existing dislocation, to add to the existing plastic deformation, you need to increase the amount of stress. And since in the creep condition you have a constant stress, you cannot increase the stress. Consequently, what you essentially have is the decrease in the creep rate or in the decrease in the rate of deformation. And that is the reason why we have a decelerating creep in the transient stage. Now, the stage that precedes the steady state condition is dominated by strain hardening. You have significant amount of dislocation, and these dislocations are moving and they are interacting with each other in order to render the plastic deformation. So what happens in the steady state condition is the influence of temperature sets in. So temperature, it reduces the dislocation density. The way it reduces it is by annihilation, these we saw earlier, and the other way is that it through polygonization. So one is when the temperature sets in, the mobility of the dislocation is enhanced, and because of the mobility, even though the mobility favors plastic deformation, and because of the mobility, these dislocations, the interaction, the probability of their interaction increases and they annihilate each other, thereby reducing the number of dislocations. And similarly, at high temperature, since in addition to the glide event of the dislocation, the movement of the dislocation, propagation of the dislocation, which we refer to as the glide, in addition to the glide, since at high temperature the climb is also possible, we can rearrange the dislocation in such a way that you create a subboundary and thereby reduce the number of active dislocation that leads to plastic deformation. So by reducing the number of dislocation, that is through annihilation and through rearrangement, that is forming a new subboundary which comprises of the dislocation. So by reducing that, you have essentially reduced the amount of plastic deformation in the steady state condition. In case of the transient creep, you have a significant increase in the plastic deformation, and therefore a significant strain is observed. However, in case of steady state creep, you have reduced the dislocation density significantly either by annihilation, or the more amount of dislocation is lost through rearrangement or polygonization, which leads to the formation of subboundaries. Now, this is one of the reasons why you observe a decrease in the creep rate at the steady state condition or in the steady state condition. Now, our intention is to further reduce the creep rate in the steady state condition. We want to further reduce the amount of plastic deformation observed in the steady state condition. So that is our aim. So when we do that, we ultimately increase the life of the material. So let's first see from where does the marginal strain that we see in the steady state condition comes from. So we have already annihilated a significant amount of dislocation that contribute to the transient creep. So those we have done by annihilation and the polygonization or rearrangement. So through these events or through these factors, we have significantly reduced the number of dislocations. However, there are some dislocations that are present, and these dislocations, they continue to glide and climb. And this is what leads to the marginal strain that you observe in the steady state condition. So let me repeat, when you consider the plastic strain, it is proportional to the amount of dislocation that is present, that is the dislocation density, and the average distance that is covered by the dislocation. So the plastic strain is contributed by two factors, that is the number of dislocations that are present and the average distance covered by these dislocations. Now, when you increase, or when at the steady state condition, you have a significant increase in the dislocation, and therefore you observe, or rather in the transient state, in the transient state, you have significant increase in the number of dislocation, and therefore you have a significant increase in the plastic strain. However, when you move into the steady state condition, you reduce significantly the amount of this particular term here is significantly reduced, that is the amount of dislocation density is significantly reduced, and therefore the number of dislocation that contributes to the plastic deformation is reduced, and therefore you see a decreased creep rate in the steady state condition. However, there are some dislocations that are still available, and these dislocations, they increase or they contribute to the plastic deformation through their mobility. So these dislocations that did not annihilate or that did not rearrange, they still propagate, they still move, and by the change in the average distance covered by the dislocation, because of this average distance, increase in the average distance covered by the dislocation that has not been consumed by annihilation or polygonization, this factor here contributes to the plastic deformation or the observed deformation or observed strain in the steady state condition. So what we have is, in this steady state condition, even though there is a marginal or minimal strain, there is a strain associated with the steady state condition. So this strain is not caused by increase in the dislocation density, because in the dislocation density is significantly reduced by annihilation or rearrangement at the steady state condition. However, the existing dislocation, they keep on moving either through slide or rather glide and climb. So the existing dislocations, they continue to glide and climb, thereby increasing the average distance covered by the dislocations. So this increase in the average distance covered by the dislocation ultimately contributes to the contributes to the strain observed in the, or it could be minimal, but still there is a strain observed in the steady state condition. Now our goal is to reduce this average distance that is covered by the dislocation, thereby reducing the plastic strain. So once if we are able to reduce the average distance covered by the dislocations, then we will be able to reduce the plastic strain. And on top of it, it's more important to know that if we are able to reduce the rate at which these dislocations are propagating, if we are able to hinder these dislocations in such a way that the rate at which the dislocations are propagating, then we can also hinder the rate of creep at the steady state condition. So let me repeat, we saw first by reducing the average distance covered by the dislocation, we can reduce the amount of plastic strain. Since our discussion is based on creep, since we are largely considering the time dependent deformation, now in our context, instead of reducing the overall average distance, we are more interested in reducing the rate at which this distance is covered. And if we are able to impede the propagation of the dislocation so that the rate of propagation is minimal, then the creep rate will also, particularly in the steady state condition, will also be minimal. So once you have a minimal creep rate, that is further reduced from the already minimal one. So you already have a minimal creep rate and you are further reducing it by obstructing the propagation of the dislocation and by reducing the average distance covered by the dislocation, then you have essentially reduced the plastic strain at a given instant. You have essentially reduced the creep rate in the steady state condition, thereby enhance the life of the material at high temperature. So one way of enhancing the life of the material at high temperature is to impede the propagation of dislocation in such a way that the rate at which the dislocation glides or climbs, the rate at which the dislocation propagates is reduced. Now one way of doing that, so this mechanism is important, or one of the important mechanisms of achieving this reduced rate of propagation of dislocation, thereby decreasing the creep rate, is solute solution strengthening. Solid solution strengthening. So our goal is to enhance the life or increase the life of the material, and that can be achieved by increasing the time spent by the material in the steady state condition. And in the steady state condition, if you are to increase this time taken by the material in the steady state condition, what we essentially need to do is reduce the plastic deformation at a given instant in that steady state condition. And to do that, if we are able to reduce the rate at which the dislocation propagates, then essentially it is possible for us to reduce the rate at which the plastic deformation is observed in the steady state condition. Now, one way of doing that is solute solution strengthening. Now, the solute solution is a term that is that we as metallurgists are familiar with. So what essentially you are doing is you treat a base metal as a solvent, and in that the alloying element is treated as the solute. So what essentially you are doing is similar to the solutions that you have in terms of the liquid, you are creating a solution in terms of the solid. And this term solid solution, it all it's all based on the solubility of the newly added solute onto the solvent. So similar to the liquid solution, you are making a solid solution. Here the solute solution, the solvent is the base metal and the solute is the alloying element. Now, since we are talking not in terms of alloys but in terms of solid solution, we are essentially concerned with the solubility of the solute in the solvent. So when you talk about the solubility of the solute, you have to go back to a law that governs the solubility, which I guess by now you would have guessed. This is the Hume Rule 3 law. This law tells us how much, or this law dictates what are the factors that govern the solubility of the solute that you had to the solvent, that is the base metal. So when you add an alloying element to a base metal, so the solubility of that base metal is governed by, of that solute with the base metal is governed by several factors, and this Hume Rule, it compiles all these factors. And one of the factor is the difference in the atomic size. So we want to enhance the creep material or the life of the creep material, and we want to enhance the life of the creep material by reducing the creep rate in the steady state condition. One way of doing that is reducing the rate at which the dislocation propagates or impeding the proper path of the dislocation. Now we want to do that by introducing some solutes, that is the nothing but the alloying elements. You want to introduce that to the solvent, that is the base metal. So by introducing this, we want to reduce or impede the propagation of the alloying element. Now, since we are talking in terms of solid solution, there are several factors that governs the solubility of this solute in the solvent. So one of the factor is the atomic radius. So if AX is the atomic radius of the solute that you are adding, and AM is the atomic radius of the base metal, then the difference in the atomic radius, when you translate into the percentage, should be less than 15% for the solute atoms to be comfortably placed in the lattice of the solvent. Let me repeat, when the difference in the atomic radius of the solute and the solvent is less than or equal to 15%, then the solute atom can be comfortably placed in the lattice of the base metal. So that means you have achieved a good solution, a solution wherein the solute atom is comfortably sitting in the place or comfortably replacing the base metal or the atoms of the base metal. So this we refer to as the substitutional solid solution. And similarly, if, or rather in contrast to the rather comparable size of the atoms of the solute and solvent, if the size of the atoms of the solute is significantly lower than the size of the base metal or size of the atoms of the base metal, then these atoms of the solute, they dissolve in the base metal by not replacing the atoms of the base metal but occupying the interstitial positions. Now, when the atomic size of the solute is significantly lower than that of the atomic size of the base metal, then in this case the atoms of the solute, they occupy the interstitial position that we refer to as the interstitial sites, and this solution is referred to as the interstitial solid solution. So we want to strengthen the material, or we want to enhance the creep life of the material by introducing solutes, and the positions of the solute, the place where these solutes are being placed, or the positions, or rather how these solutes dissolve in the base metal, it depends on one factor that governs is the size of the material or size of the atoms of the solute. When the size is comparable, less than 15% or close to 15%, the atoms of the solute occupy the lattice points that is meant for the base metal. If not, if it is very small, then the solute atoms, they occupy the interstitial sites of the base metal. So these both substitutional, or both these differences in the atomic sizes, a comparable atomic size and significant difference in the, or a significant disparity where the atomic size of the solute is much smaller, both these leads to solid solution, but one leads to substitutional solid solution, the other leads to interstitial solid solution. Now we want to know how this introduction of the solute, it impedes the propagation of the dislocation, because we are concerned with impeding the propagation of the dislocation, or at least reducing the rate at which the dislocation propagates. Now, how does the introduction of the solute impedes the propagation of the dislocation? Now, we saw when you have the size of the atoms that are comparable, then you have the formation of substitutional solid solution. So it is very rare that you have the atomic size of a solute that is close to that of the atomic size of the base metal. It is very rare. So what happens is generally there is a significant amount of difference in the atomic sizes. Now, the condition for the Hume Rule 3 rules is for the solubility. However, it is possible for the atoms that wherein the difference is greater than the 15%. So the Hume Rule 3 rule states that when the atomic size, the difference in the atomic size is equal to or less than 15%, you have a comfortable amount of solubility. However, when the difference is larger, what is compromised is the solubility. It does not mean the atoms with the largest size cannot occupy the lattice points of the base metal. They can occupy, but the solubility is compromised. Now, our focus is not to enhance the solubility, but to enhance or to impede the dislocations or the migration or the movement of the dislocation. So if you talk in that terms, it is possible for us to have solutes which have a size that is greater than the 15% or the size that is greater than the difference in the atomic size or 15% difference in the atomic size. So we can have the solute, we can introduce the solute that are significantly larger than the atomic size of the solvent or the base metal. Again, the reason we want to do that is we are not interested in increasing the solubility, but we want to impede the propagation of the dislocation. Now, when we in some conditions violate the Hume Rule 3 rules, the amount of solubility will decrease. However, there will be atoms, the larger atoms of the solute occupying the lattice of the base metal. So what essentially happens is your base metal or the lattice of the base metal at some instances are replaced by atoms, larger atoms of the solute. So the Hume Rule 3 rule is based on it's the condition that dictates the solubility. We are not interested in the solubility. So what we are essentially doing is we are essentially introducing atoms, solute atoms that have size that is larger than the atomic size of the base metal, and they also violate to some extent the Hume Rule 3 rule. So of course, when you violate the Hume Rule 3 rule, the solubility is decreased, but still you have some amount of these larger solute atoms occupying the lattice of the base metal. So when you have the larger solute atoms occupying the base metal lattice, you introduce a significant amount of distortion. So what essentially we are doing is we are introducing distortion in the lattice by introducing solute of larger atomic size. We have a solute of larger atomic size, and this solute, by introducing it, we are creating a distortion in the lattice. Now of course, you can create a distortion in the lattice by sticking with the Hume Rule 3 rule. However, the amount of distortion that is created by the larger atom will be significantly higher, and therefore we are not much worried about the Hume Rule 3 rules. However, even though it governs the solubility, we want to some degree violate it, because by violating it, even though we are compromising on the solubility, we are increasing the distortion. So what essentially happens when you increase the distortion is that there is an elastic interaction that occurs between this distortion and the dislocation. Now, if you could recollect, when we talked about the defects, particularly the point defects, vacancies and interstitials, we saw that one effect of the temperature is to increase the equilibrium composition or the stable composition of the vacancies. So that means at high temperature, the number of vacancies will be high, and they are stable. They are not disturbing the equilibrium condition of the system. However, when we talk about the dislocation, they increase the energy of the system. The dislocation, they have a strain energy surrounding it. They also distort the lattice. So be it edge dislocation, be it screw dislocation, or be it combination of the dislocation, they also distort the lattice. They also bring about the distortion. So what essentially we are doing is we are letting the distortion that is created by the dislocation to interact with the distortion that is created by the newly added solute atoms, which are larger than that of the base metal. And so because of this interaction, the propagation of the dislocation is impeded. So thereby we are reducing the plastic strain at a given point. So one way in which the solid solution achieves the reduction of the plastic deformation is by impeding the dislocation through this elastic interaction. So what we mean by this elastic interaction is this solid solution, when the atoms of the solute that you are adding, when they are significantly larger than the base metal, so even though they might violate the Hume Rule rule because of their size difference, even though because of their largeness the Hume Rule rule might be violated, the distortion that they bring to the lattice is significantly increased because of the largeness of their size. So this distortion again, it creates an elastic field around it. This elastic field will interact with the elastic field that surrounds the dislocation. So you have a distortion that is created by the solute, and there is an increase in the strain energy because of the solute now, and you also have a dislocation that is coming towards it that has its own distortion surrounding it. It brings its own distortion to the lattice, to the overall lattice of the system. So both these distortion they interact with each other, and this interaction impedes the rate at which the dislocations propagate. And therefore, because of the distortion that is introduced by the solute, we have achieved, or we have impeded the rate at which the dislocation propagates. So it is the elastic interaction between the distortion introduced by the solute atoms and the distortion that is already associated with the dislocation. We've been able to impede the rate at which the dislocation propagates. Now, this all the discussion so far we had is confined to the substitutional solid state solution, and particularly when the size of the solute atom violates the Hume Rule rules. However, the same is also possible when it is within the Hume Rule rules, and since when you comply to the Hume Rule rules, the amount of solubility increases, then you have an increased amount of solute atom that is present and the increased amount of distortions, but these distortions are rather dispersed, and therefore the effect of the distortion is more pronounced when you violate the Hume Rule rules. So what we mean by that is, supposing you stick with you comply with the Hume Rule rules and introduce a solute that is the difference of which is within the 15%, the difference of the atomic size of the solute and the base metal are within 15%, you increase the solubility. And by increasing the solubility, you then replace significant numbers of the base metal atoms with the solute atoms, and each come with their own distortion. And since you comply to the Hume Rule rules, the distortion that is brought is rather minimal and they are dispersed. Therefore, the interaction will also be minimal and they will be dispersed, and the dislocation, even though they are impeded to a certain degree, they can easily pass through. However, when you violate the Hume Rule rule, then even though only small number of solute is present in your system, it completely is soluble in your system, the distortion it brings about is significantly high. And therefore, the interaction will also be significantly high, and significantly your dislocations will be impeded. So, when you comply to Hume Rule, the distortion is rather dispersed. So the distortion is rather dispersed, and the degree to which you impede, even though you impede your dislocation moment, the degree to which you impede is rather compromised. However, when you violate the Hume rule, then your distortion is increased and it is confined. And in that case, the amount to which you impede your dislocation will be higher. So therefore, it is better to violate the Hume rule and to have a small amount of solubility of your solute than to comply with the Hume rule and to have a significant amount of solubility and corresponding distortion. Now, all these discussions have been so far confined to these substitution solid state solutions. Now, in addition to the substitution solid solution, we have the interstitial solution, interstitial solid solution. So in case of interstitial solid solution, there is also a distortion that is brought about in the lattice by the atoms that occupy the interstitial site, and even these distortions, they interact. So when compared to the solid solution that comply with the Hume Rule rule, that violate the Hume Rule rule, and the when you compare both these two, that of the interstitial solid solution, of course the distortion is rather compromised or it is reduced. So correspondingly, the degree to which the dislocation is impeded is also decreased. So when you add the solute, or when you create a solid solution, you rather create a substitution solid solution or the interstitial solid solution. Both they introduce as distortion in the lattice parameter or lattice of the base metal, and this distortion through the elastic interaction impede the propagation of the dislocation. And if you want to say which one brings the maximum or restricts the maximum restricts the mobility of the dislocation to the maximum, it's the substitutional solid solution that violates the Hume Rule. So it's the substitutional solid solution that violates the Hume Rule that brings the maximum distortion, and it's the one that restricts the propagation of the dislocation to the maximum. Secondly, it is the substitutional solid solution that complies to the Hume Rule. So this also creates a distortion, and this also impedes the propagation of the dislocation, but it is to a degree that is less than the substitutional solid solution that violates the Hume Rule rules. And finally, you have the interstitial solid solution. Even that creates a distortion, and that also will impede the propagation of your dislocation. In addition to the degree of the restriction that is imposed on the dislocation depending on the nature of your solid solution, the elastic or the distortion that each of the solid solution create is also different. In case of substitutional solid solution, you introduce a spherical distortion, and in case of interstitial, you introduce a non-spherical distortion. So this is just a difference between the way the distortion is brought about by the substitutional and interstitial solid solution. So what we have essentially seen is it is possible for us to enhance the light temperature life of the material by decreasing the plastic deformation the material experiences within the steady state condition at a given point. So this one way of doing that is introducing a solute, and this solute, it introduces a distortion to the lattice of the base metal, and because of this distortion, the propagation of the dislocation is impeded, because this distortion that is brought about by the solute should interact with the distortion that is brought about by the dislocation. And that is the reason why because of this complex interaction, the rate at which the dislocation propagates is impeded. Now, even though this principle remains the same, there are different degrees to which these solutes impede the dislocation. So the substitutional solid solution that is created by the solute of comparable size, when it violates the Hume Rule, it significantly impedes the moment of the dislocation. However, the interstitial solid solution, when the solute size is significantly lower and occupies the interstitial site, the distortion is non-spherical in nature, and the degree to which it impedes is compromised or minimal. Between these two stand the substitutional solid solution that complies to the Hume Rule. So even though this solid solution or the amount of solute in this solid solution will be higher, the distortion introduced by it will be lower and dispersed, and therefore the way it impedes the dislocation is not as significant as that of the substitutional solid solution that violates the Hume rules. So this is one way of enhancing the life of the material. So we will see the other ways in the subsequent lecture, wherein we will consider the ways we can enhance it by working on the microstructure of the material. So let's see ourselves in the next lecture, wherein we will consider other ways of enhancing the high temperature life of the material. Goodbye.